You pour a fresh cup, take a sip, and the flavor is unpleasantly sour, or worse, it tastes like bitter ash. Most homebrewers assume they've simply burned the coffee with boiling water. The logic is that extreme heat over-extracts every compound at once, destroying the flavor profile. But coffee science reveals a contradiction. Light roasts actually require water right off the boil to taste their best, while dark roasts require significantly cooler water to remain drinkable. This raises a problem for the standard brewing routine. Why does the exact same water temperature produce bright fruit notes in one roast and the flavor of burnt vinegar in another? The explanation is found within the bean's hidden matrix of organic acids and the specific structural changes that occur during the roasting process. To understand why temperature matters, we have to look inside a raw, unroasted green arabica bean. At this stage, the bean is packed with complex organic acids, specifically citric and malic acids, which provide sweetness and tartness, alongside a large volume of chlorogenic acids. Roasting changes this chemistry through intense heat. As the temperature rises, gases expand, causing the bean to crack and its cellular structure to stretch. A light roast stops early. This preserves the original citric and malic acids and leaves the bean's dense cellular structure mostly intact. Dark roasting, however, destroys those initial fruit-like acids. In their place, the heat creates high concentrations of acetic acid, the primary component of vinegar, and bitter quinic acid. This data shows the shift clearly. While green coffee has a low baseline of acetic acid, the concentration spikes as the roast progresses toward dark, nearly tripling in some samples. Dark roasting also has a physical consequence. The prolonged heat weakens and degrades the cellulose that makes up the bean's cell walls, making them highly porous. The degree of the roast dictates which acids remain inside the bean and how easily those acids can escape. During brewing, water temperature acts as a selective filter. It determines which specific compounds dissolve into your cup. Water above 96 degrees Celsius has high kinetic energy, rapidly dissolving heavy, aggressive compounds like bitter acetic acids. Dropping the temperature to 85 degrees changes the extraction, lacking the energy to pull out harsh molecules, favoring delicate acids instead. Adjusting the temperature allows a brewer to choose a specific chemical profile from the exact same coffee grounds. When we combine these two variables, the reason for the temperature shift becomes clear. The bean's physical state determines the thermal energy required to reach the good flavors. In a light roast, dense cell walls act as a structural barrier, trapping sugars and citric acids within a rigid matrix. To reach those compounds, boiling water provides the high thermal energy needed to penetrate the barrier. Without it, coffee tastes weak. A dark roast bean is structurally fragile. Its cell walls are shattered, leaving harsh acetic acids completely exposed. Because the structure is weak, boiling water instantly flushes bitterness into the brew. Cooler water slows extraction, harvesting sweetness without dislodging harsher elements. High thermal energy is required to penetrate dense beans, while gentle heat is necessary to protect the balance of fragile ones. Over-extraction is essentially a mismatch between the physical fragility of the bean and the thermal energy of the water. If a cup is overwhelmingly bitter, it is a sign that the water temperature was too aggressive for the specific acids present in that roast. The type of coffee matters as well. This comparison shows that dark roast Robusta contains significantly more total organic acids than arabica, making it even more sensitive to temperature mistakes. Achieving a balanced cup requires looking at the roast level first, then intentionally dialing in the target temperature to match that bean's chemistry. Brewing coffee is the act of performing a precise, intentional chemical extraction.